So we would like to establish that if we have a Banach space Y, so Y is complete, then the norm linear space of bounded linear maps from any norm linear space X into Y is complete. Therefore, it's a Banach space. So we have established that it's a norm linear space. It's enough to show completeness. So let T sub n be a Cauchy sequence of operators in B of xy. Then for every x in X, we have T sub n minus T sub m as an operator of X in norm is less than or equal to T sub n minus T sub m times X. That's what happens with norms of, that's how the norm of an operator works. Yes, but the left-hand side can be interpreted as T on n sub X minus Tm sub X. And this is less than or equal to T sub n minus T sub m. Yes, but if T sub n is a Cauchy sequence, then that means that this tends to 0 as n comma m tend to positive infinity. So of course we could say that, the usual story that for any epsilon greater than 0, there exists a node, so that for n comma m, this the norm of this difference is less than epsilon. The bottom line is that this implies, since this is a constant, so if we fix, so I should have said yes for every, but for fixed, but arbitrary in some sense, X in X, we have this series of inequalities, and this implies that Tn sub X is, for n in n, is a Cauchy sequence. Yes, but it's a Cauchy sequence where? In Y, which is a complete norm linear space, or a Banach space. Since Y is complete, Tn sub X converges, and define T of X by the limit as n tends to infinity of Tn of X. Okay, then we can easily check that this is linear, because, this is standard limit property. So T of x1 plus x2 is, by definition, the limit as n tends to infinity of Tn of x1 plus x2, which is the limit as n tends to infinity of Tn of x1 plus Tn of x2. And it's very easy to show, it's as easy as it is to show it for real numbers, that in a norm linear space, the limit of the sum of two sequences is the sum of their limits, as long as those sequences converge. So this would be T limit as n tends to infinity of Tn of x1 plus limit as n tends to infinity of Tn of T2, I'm sorry, this is T1 of xn, and this is T2 of xn. Let me clean it up and write it in a decent way. Okay, so this is T1, Tn of x1 and Tn of x2. And this will be T of x1 plus T of x2. And that shows that it's additive. The homogeneity of the operator is proven exactly in the same way. So it's a linear map. Now, it's interesting to see that in any norm linear space, we have this inequality. Actually, maybe we should show this in a quick video somewhere else, which implies that the sequence of the norms is a numerical Cauchy sequence. And the reason I'm saying this is because Tn of x is less than or equal, its norm is less than or equal to the norm of T of n times x. And if we pass to the limit on both sides, we will find that T of x is less than or equal to the limit as n tends to infinity of Tn times x, which means that T is a bounded linear operator. And the last thing that we need to show is that Tn tends to T in B of xy. So this is done in a standard way using the fact that Tn minus T is the supremum of Tn of x minus T of x for x less than or equal to 1. So since n at Tn is Cauchy, for epsilon greater than 0, there exists an n naught in n such that if n comma m is greater than n naught, then T sub n minus T sub m is less than epsilon over 2. And this means that for x with norm less than or equal to 1, Tn minus T of x is less than epsilon over 2. And I'm sorry, T sub n minus T sub m is less than epsilon over 2. And if we pass to the limit, so if we keep n fixed, and pass to the limit as m tends to infinity, we get that T sub n minus T of x is less than or equal to epsilon over 2 for n greater than n naught, and for every x less than or equal to 1. This means in particular that T sub n, which is the supremum of all these, minus T is less than or equal to epsilon over 2 for n greater than n naught, which implies that Tn minus T is less than epsilon for n greater than n naught. So to make a long story short, this means that we started with an epsilon greater than 0, and we showed that there exists an n naught, so that for n greater than n naught, we have t sub n minus t norm less than epsilon. So this means that Tn tends to t, and that means that t is the limit inside b of xy of the Cauchy sequence t sub n. That means that p of xy is Banach. And of course, again, we need to emphasize that the only thing that we needed here is that y is complete. It can be shown actually that if X is a non-zero linear space and non-trivial linear space, then the reverse is complete, that if b of xy is Banach, then y is Banach, but we don't really need any of this, so we will leave it at that. So that gives us a whole new class of Banach spaces, and we will see that we will be interested in the specific case that Y is a very, very simple space. But we will leave this for another video. And that's all. Thanks for watching.